Okay, so if we're not going to really look at the series today, but we're going to focus a lot on the sequence. So you need to know what a sequence is, and a sequence is just a list of numbers. So if you look at questions 7 through 15, those are all sequences. Just a list of numbers. And then they don't have to, but they often have a pattern to them, or come in a pattern. Because without a pattern, it's not predictable, and if it's not predictable, then it's pretty hard to apply to real world situations. So, for that reason, most everything we look at will come in some kind of pattern. So there are two very, very common types of sequences that you will need to be able to identify, name a characteristic of for each one, and be able to write formulas for. And that is arithmetic sequence and geometric sequence. Arithmetic sequence is when you add the same thing at each step. So you get from the first item to the second item, you add something, and you add that same something, you get to the second to the third, and the same something, you get to the third to the fourth, etc. And you might also want to put in parentheses here, this would include subtract, because adding a negative number is the same as subtracting. And that thing that you added each step is called common difference, and we refer to that as variable D, common difference D. So common difference D is that thing being added each time. Now, not all sequences have to fit these two patterns, but these are going to be the two most common. And then the other one is geometric, and this is when you multiply by the same thing. At each step. And you may want to put in parentheses that can include division, because you can multiply by fractions. Multiplying by a half is the same as dividing by 2. Multiplying by a third is the same as dividing by 3. So if you see that you're multiplying or dividing at each step, that's going to be a geometric sequence. So a geometric sequence has what's called a common ratio. So we use the variable r. And r is going to be that thing that's being multiplied at each step. So other than identifying these and stating what the common difference is, what the common ratio is, we also like to use these as formulas. With the formula, it allows us to predict what's going to happen, and that builds into the series piece where we add a bunch of these terms together. So probably the more useful of the formulas, because we got to do two today. Implicit and recursive. We won't talk about recursive until we get to the third page. But an implicit formula is going to be set up like this. It's going to say a sub n equals, and then what it equals just depends on the actual sequence. But it's set up in a way so that if you plug in for 1, it's supposed to give you the first item of the sequence. And when you plug in 2 for n, the formula is supposed to give you the second item. If you plug in 3 for n, the formula is supposed to give you the third item. And then the idea is that if you want to know the 56th term, that you're actually figuring out the 56th term manually, but you're plugging 56 in for n into the formula. Okay, so question 7 through 15, let's put a couple of these together so you can see what you're looking for, and there's a few that I'd like you to do. Question number 7, to go from 1 to 3 to 5 to 7, looks like it's adding 2 each time. So the next 3 items would be 7, 11, 13. Put that dot implies that it continues to go. Now, you don't really have to say whether you think it's arithmetic or geometric, because you need to state the common difference or state the common ratio. So if you say R equals, that tells everybody that you think it's geometric sequence. If you say B equals, then you're saying it's implied that you think that it's arithmetic. So in this case, B would be 2, because that's what you're adding each time. Okay, number 8, you can say that to go from 2 to 4, you're adding 2, but then you don't add 2 again to get to the third step, so that one's not arithmetic. You can't tell this from 2 terms. You need to see what now. To get from 2 to 4 to 8, looks like it's multiplying by 2 each time. And if you're multiplying by the same term, it's geometric. And geometric is a common ratio, so we say R equals, and what you're multiplying by is what R is. There's half my answer, and then we also need to list the next 3 terms. Times 2, times 2, times 2, and then dot, 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 to show that it does keep going. Okay, number 9, to get from here to here, there's something I could add. There's also something I could multiply, so that looking at the first 2 terms is not enough to determine what type of sequence it is. But if I go from here to here, looks like it subtracted 10, then it subtracted 9, then it subtracted 8. So it's not adding the same thing each time, so it's not arithmetic. But it's also not multiplying the same thing each time, so it's not geometric. So it's just neither one of those sequences. Not that there's not a pattern to it. It just doesn't fit one of those nice neat ones that you're going to be very familiar with. Okay, so I would like you to do this on the next 6. Can I give you like 3 minutes to do that? And then I will pick 2 of those to go over and let you compare to check and understand. So the two that I will pick are the ones that are just maybe just a touch different than what we looked at. Like 11. From here to here and here to here, you're dividing by 2 each time. It doesn't mean that the common ratio is 2. If you're saying that the common ratio is 2, it means you're multiplying by 2. So a different way to achieve the same goal is to say that the common ratio is a half. Because multiplying by a half is the same as dividing by 2. So your next 3 terms should be 12.5, and then 6.25, and then 125. And of course we could keep going if we needed to. Cutting it back each time, smaller and smaller time. And also check number 13. Looks like it's going down 4, going down 4, so it is adding the same thing each time. It's adding a negative 4. Adding a negative 4 is the same thing as saying that it adds, or subtracts 4. So, subtract 4 more, and then 4 more, and then 4 more. Okay, so if you made a mistake on those two, it's very likely you need to check some of those others as well. But I will help you with those when you get some independence on those. Okay, so let's move on. Some of this chart asks you some of the same things because we're building upon this. And then we're also going to kind of squeeze in how to write the explicit formula and then how we're going to use that to do this in a much easier way, much more efficient way. So when I look at this one, we get from 6 to 12 to 24. I can tell it's multiplying by the same thing each time, the geometric, which means it has a common ratio. We get from 6 to 12 to 24 would be 2, but how is it going to alternate between negative and positive and negative like that? The common ratio needs to be negative. Negative 6 times negative 2 becomes positive. Positive 12 times negative 2 becomes negative. So anytime you see the signs alternate, it's just that your common ratio needs to be negative. Okay, so our explicit formula is going to be set up like this, a sub n. And then we've got to come up with a formula so that if we plug in 1 for n, the formula gives us negative 6. But then if we plug in 2 for n, it gives us 12. If we plug in 3 for n, it has to give us negative 24. So that way we can see it's going to work for everything else past that. I didn't really give you much space, so I would squeeze this in down here. I really think we should break this out. There's a formula for a geometric sequence, an explicit geometric sequence. And this is good because we don't want to mentally have to come up with some formula. We don't want to have to mentally think about what formula is going to make all that work. So for geometric, there will always be a sub 1, which means the first term, which is when n is 1. So for us, that is negative 6 times the common ratio, and then the exponent on the common ratio is n minus 1. So first term, base of 1, times the common ratio, and then the exponent on the common ratio is n minus 1. Now, as long as it's geometric, you don't have to worry that that works for this question, but maybe not the next question. It will always work for geometric. To convince you, I want to plug them in, all of them in for each of these today. But notice, if I plug in 1 for n, think about what's going to happen before I put enter. That's going to make the exponent be 0. Anything to the 0 power is 1. And then negative 6 times 1 is going to be negative 6. So plugging 1 in for n gives me the correct first term. If I plug 2 in for n, now this exponent is going to be 1. So I end up with negative 6 times negative 2, which gives me the positive 12 second term. And then if n is 3, it's just multiplying by another negative 2, because there's one more negative 2, and you can see that that works. So one of the biggest uses of this, at least for today, is if you want to know the 10th term, that's what a sub 10 means, I mean, can you extend this pattern times negative 2, times negative 2, times negative 2, times negative 2? You can manually do that, but no one wants to do that. Instead, use the formula and plug in 10 for n, and let your calculator do the work. The 10th term would be 3,072. So here's another geometric, so we can say the same thing again, maybe a little bit quicker this time. Times 3, times 3, times 3. Multiply by the same thing each time. It's called geometric. And its explicit formula will always be a sub n equals the first term. That's what a sub n means. Times the common ratio. The exponent on the common ratio is n minus 1. Always use n minus 1. You use this structure, it will always work if it's geometric. Again, you can plug in 1 for n and see that it gives you 1. And you can plug in 2 for n and see that it gives you 3. I'm not going to do that this time. I did that last question. But if you want to know the fifth term, if really that's your only goal, then I guess it probably makes sense to not even do the formula, right? Times 3 times 3 times 3. That's the next one's supposed to be. But it's also good for you to see that the formula gives us the same thing. Putting in 5 for n also gives us 8. Alright, the next one is not geometric, so it's not going to have the same type of formula for explicit. This is add 2, add 2, add 2, so it's adding the same thing each time. Which makes it arithmetic, and makes the common difference be 2. You should write down an example down here. So it's also going to be, say, a sub n equals, when we say n, we're just saying a generic number n, whatever number you want to plug in there. N, generic number. Okay, now I'm a little different on this. Like, I can look up a more formal definition for you on this, but I don't think the formula is set up in a way that is very intuitive. So instead, what I recommend is that you do the common difference times n. And now this is, you can think of this just like slope. Whatever the slope is, as n keeps increasing by 1, it's going to go up at that same rate, which is what we want. Then, doing it this way, you need to either add or subtract something, and it depends on the question. So let's go back up here and look at what I'm saying. So the a sub n equals 2n. It's common difference times n. So I'm saying this has a slope of 2. Notice this has a slope of 2. This changes at a rate of 2. Add 2, add 2, add 2. The problem with this being your formula is that it doesn't work right now. If I plug in 1 for n, I get 2. If I plug in 2 for n, I get 4. If I plug in 3, I get 8. If I plug in 4, or if I plug in 3, I get 6. And if I plug in 4, I get 8. So all of those are off by the same amount. So you really only have to figure it out for the first one. If I plug in 1 for n, I get 2 right now, but it's supposed to be 12. Or it's supposed to be negative 10. So it is 12 off. So just subtract 12. This makes sure that it starts at the right location. This makes sure that it goes up at the right rates. So for this one, I'll plug in a few to help you see that it does work. That's when n is 1. When n is 2. When n is 3. When n is 4. So if you want to know when n is 56, if you want to know the 56th term, then plug in 56 for n. It looks like the 56th term is behind. Not that you couldn't do that manually, but you certainly wouldn't want to do that. Okay, let's look at one more arithmetic to help you see where this minus 12 came from. So we need to skip down to maybe this one. This one adds 8, adds 8. Those arithmetic common differences of 8. So I want this to change at a rate of 8. So that's very similar idea to slope. Now, sometimes this might be good. It might be done, but more than likely not. You need to test and see how far off you are. You plug in 1 for n, you get 8 currently, but it's supposed to be negative 31. So how far off is that? It's 39 off. It's 39 too big, so subtract 39. That should make sure that it hits the correct first term. And then this will make sure that it goes up by 8 and goes back up by 8. And anytime that you're unsure, it doesn't take very long. Plug in 1, see that it works. Plug in 2, see that it works. And plug in 3, see that it works. So if you want to know the 32nd term, as long as your formula is set up correctly, you should just be able to plug in 32, and we can predict this is going to be 272. So just to give you some insight, even though that you can do this manually, when we get to series next class, we're going to not just want to know what is the 32nd term, but we're going to want to know what are the first 32 terms added together. So still something you could do manually, but it would be even worse. You don't want to find all 32 terms just to have to add them up. This formula is going to come out of you will need to be able to write that formula and write that next class. I would like you to practice one of each of these. So you would try this one and this one. Try the whole row there for those two questions. Those will be the two that I go over and let you check with. The others you can get a little started on, but I'll ask you to come back and do those for extra practice at the end of class. Alright, so of those two, the first one is arithmetic. And the common difference is negative 24, because you're subtracting 24 each time. Arithmetic is the one that you do need to put a little bit of fun into the formula. It'll be the common difference times n. It's like its slope. That's a rate that it's changing. But this alone doesn't start off at the right spot. Plug in 1 for n, currently get negative 24, but it's supposed to be 72. So you can think about that is 96 off. 96 too small. So just add 96, and now it should start at the right location. And this measure that it grows or decreases at the right rate. I will plug it in to make sure. First term works, second term works, and third term. By the way, I know I said this a long time ago, but this is kind of helpful here. Like if you do want to test this, and you type out the formula and you plug in 1 for n, remember you can just hit second enter, and it pulls up what you just typed in, and then you can just go change it to 2, second enter, go change it to 3. Then it's easy to, if you really want to type it in once. Okay, so then if you want to know the fifth term, you could do this one pretty easily manually. Subtract 24, subtract 24. That is very reasonable. But it's also good for you to see that plugging in 5 to the formula will achieve the same thing. Alright, down here, this one was geometric. Sometimes if you suspect that it's geometric, but you're not sure what the common ratio is, just take the second term divided by the first term, and that would be 6. And then you can see if this is times 6, is this times 6? Okay. In this formula, you don't have to think about as much, but you do need to memorize the expression. It's always going to be the first term times the common ratio to the n minus 1. So if you want to know the 8th term, plug it in, and I'm getting this.
Yeah.
Why is that so much bigger? Okay, what about the formula though? No, it's only raising 6. That's okay, because this is exponential, right? You've got your variable in the exponent. So this is going to grow much, much faster. It's an exponential equation like we just talked about. This arithmetic equations are linear. Linear grows very, very slow. Plugging in 32 and it didn't even grow very much. Plugging in 8 and it's already over 1 million. So think about how those formulas are set up. Okay, the second page has a lot of the same information, but in the opposite direction. So it's like giving you the sequence, giving you the first 3 or 4 terms, and asking you to come up with the formula, asking you to come up with what type, still asking you what type, but it's asking you to come up with the first couple terms, and it's giving you the formula. So, I hope, at least after a few of these, you might look at these and recognize that it does fit one of the 2 patterns. So I really hope that you eventually see that it's either arithmetic, geometric, or neither before you start. But if not, you just go down to here. Base of 1 means the first term. So plug in 1 into the formula to get the first term. Base of 2 means when n is 2. So plug in 2. And base of 3 means when n is 3. So plug in 3. And then if you need to look at this as first term, second term, third term, to see that it's adding 200 each time. And if you're adding the same thing each time, it's arithmetic. So you don't have to state that the common difference is 200. Directions are something you need to do that, but you need to see that. You need to memorize that. question, 29 is the same as 30, so I'm not going to make you do that one twice. So let's look at 27 now. This is a geometric, and I identify it immediately because I recognize the structure of the formula. And so I can work this one two ways. I can just plug in 1 for n, 2 for n, 3 for n, like I did on this question, and get these. Or I can think about how geometric formulas set up. This is always the first term, a sub 1. This is the common ratio, which means what you're multiplying by. So if this is the first term, multiply by negative 3 to get the second term, multiply by negative 3 to get the third term. To me, that's easy. But I also recognize the formula and I know what those parts are. Okay, and skip down to number 31. One more example before I have them practice the whole. This formula does not look familiar at all. I'm not sure what's going on with that. But that doesn't stop me from plugging in 1 for n and seeing that the first term is 3. And then I can plug in 2 for n and see that I get 5/8. Sometimes that's helpful to look at as a decimal. I plug in 2 into this formula. 2 times 2 plus 1 gives me 5. Divided by 2 cubed gives me 8. This one would be 7/27. I want to look at that as a decimal. It's about, it's equal to 2.59, and that would be perfect. So think about how much you would not enjoy it if I didn't give you this formula. I said, okay, here's your first term, here's your second term, here's your third term. Come up with a formula that fits all of those and the other ones. That would be very, very hard to do. Basically impossible. Because this doesn't fit one of those nicely patterns. This is not arithmetic, it's not adding the same thing each time, and it's not geometric, it's not multiplying the same thing each time. So maybe coming up with this formula would not be realistic to ask of you. But applying the formula, plugging in 1 for n, and 2 for n, and 3 for n, to find the first term and third term, certainly is achievable. Okay, so on this page, I'd like you to try to find one of each. So if you would do 32, 30, and 33. If you would do those first, and then the other questions on this page, I'm going to ask that you come back and do. Here in a few minutes after we finish the page. Do those 3 first, then check. Make one small mistake and you don't want to get everything. How you want longer for those three? It's fine if you do. I just don't know. You're waiting on me. Okay, so if I do them in numerical order, it looks like number 30 would be first. Again, I have a little more experience with this, so it's a little easier for me to see. And I can see that this is just kind of like what starts it off. And then as n increases, this is like the slope. So it's going to increase by 3 over 2 every time. So I can tell right off the bat it's going to be arithmetic. And that should give you 0.75. Or if you'd rather write it as a fraction, I think sometimes it's better to look at the decimal, sometimes it's better to look at the fraction. So, honestly, I would consider putting down both. And then 2.25 and 9/4. And 3.75 and 15/4. So, I don't know, I'd say probably looking at the decimals on this one's a little easier. It adds 1.5, adds 1.5. That's the same thing as saying it adds 3 over 2. So you can kind of see that in the formula if you're paying attention. Okay, the next one numerically would be number 32. So I don't recognize this right away. So that's only 1 for n, you get 2. Only 2 for n, you get 5. Plug in 3 for n, you get 10. So to go from 2 to 5 to 10, it's not adding the same thing each time, it's not multiplying the same thing each time. That's just not either, that's neither one of those two. Now, this would be an okay, this formula wouldn't be too much to expect out of you. If I gave you this and asked you to come up with that, you would have to think about it a little bit, but it is one that does do doable. And the 31, I would agree, that's a little too hard. That one would take a long time to figure out. But this one, it's always just one more than that item term squared. Alright, 33, you recognize the pattern makes it geometric. And if you recognize that, then you get a little bit of a shortcut. Base of 1 would be this number out front. You can understand 1 because there's nothing there. The common ratio is 3. So times 3 times 3. Same thing that you would get from manually plugging it in. Okay. Any question on either of those three? So you got a couple more of those, 2 more of those that I want you to go back and do. And notice this one, I didn't talk about it, we're not going to do any of these together. But these just want you to find the 10th term. So just plug in 10 for n, like we did on the front page. Find the 10th term, plug in 10 for n. 10th term, plug in 10 for n. So I know that you can do that. Okay, so the last big thing we need to talk about today is we need to talk about the recursive formula. You need to see how that's set up. And talk about how it compares to the explicit formula. So I think I've convinced you from those examples that really the benefit of the explicit formula is that it is easy to find any term in the sequence. If you want to know what the 50th term is, you plug in 50 for n. If you want to know what the 500th term is, you plug in 500 for n. That works great for the explicit formula. Unfortunately, recursive formula does not do the same thing. Recursive formula is not good for that. Recursive formula is also going to start off with a sub n equals some stuff. Stuff is going to depend on what the sequence is. And also needs this. In a recursive formula, you have to state what a sub 1 is. You have to tell the people where it's starting. And then one of the things in the recursive formula is it always is going to say, part of the formula is going to say a sub n minus 1. And you need to understand what this is saying. If you're trying to find the nth term, some generic number, n minus 1 is just the term before that, because it's one less. So a sub n minus 1 is the term before a sub n. Okay, so this looks the same as the front page, but now it doesn't say explicit formula, it says recursive. So you're still going to do this, you're still going to think about these things even if it doesn't ask you to write them down. Looks like it's adding 2 each time, so we need to identify this as arithmetic. Makes the common difference be 2. And for recursive formula, again, you have to state what the first term is. That's half of the formula. A sub 1 is 1. And then the rest of it is a sub n equals. And I guess what people like about recursive is that it kind of makes sense what I'm about to write down. If I asked you, how do you find the next term? Most of you would say, well, you take the term before it and add 2. You see that? If you wanted this term, you take the term before it and add 2. So that's how you use recursive formula. You're going to say, if you want to find this term, take the term before it and add 2. Because a sub n minus 1 just means the term before a sub n. Okay, so this one's also arithmetic, adding 3 each time. So for recursive, you need to say, all right, you're starting off at 40. You have to state that. And then you kind of get to this. This is a much better description of how you would explain it to your friend. If they said, how do you find this next term? You would probably say, take the term before it and add 3. So that's what this is trying to say. It's a term before it plus 3. One more like that, and then we need to do a geometric so you can see the difference there. This one is adding negative 10 each time. So it is a little formulaic. I mean, you can see some pattern here, but I think you should shy away from that. You should say, here's the first term, and you can find any term by taking the term before it, subtracting 10. Just a different way to describe the pattern. Let's look at how that works out for geometry. The next one's geometric, and it's multiplying by half each time. So you would still start off by saying the first term is 100, because if you only put the second line, nobody knows what the sequence is. No one knows where it starts. This only describes how to move forward. And then, if I ask you in this one, how could I find this term? You should say, well, you take the previous term times a half. So if I want to find any term, I can take the previous term times a half. And then half the half out in that place. This is a sub n minus 1. A sub n minus 1 means the term before it times a half. Just a different way to describe it. Before I have you practice this, let's talk about what's good and bad about this. What's good for most people is most people think that's an easy way to describe the sequence. Kind of makes sense if you're just saying what happens next. You're using math terminology, math notation to do that. But definitely the big disadvantage is it's not easy to find a specific term in the sequence. So the advantage of an explicit formula is not an advantage of a recursive formula. Now let's finish in this last line. If you want to know the 10th term, recursive is only helpful if you know the 9th term. It says take the 9th term and add 2 to it. If you don't know the 9th term, you can find the 9th term if you knew the 8th term and added 2 to it. But I don't know the 8th term either, so I could find the 7th term by taking the 6th term and adding 2 to it. And so finding the 10th term, unfortunately, there's not just an easy way to plug it in like there is with explicit. You basically have to do it manually. You have to say here's the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th term. And the reason why I don't care for recursive, personally, is to me, I always use explicit. You guys need to be familiar with this notation because you will see this. So if you want to find an 8th term, you just put in 8 if you had the explicit formula, but with recursive, I only can find it easily if I need a 7th term. So I'm only going to get the 7th term by just finding first, second, third, fourth, fifth, sixth, seventh, and 8th. I'm going to find the 15th term. Maybe you don't actually have to count to 15. You might see a little bit of a pattern here. First term, second term, third term, fourth, fifth, sixth, and then you say, wait, it's just going to be negative 150. Fifth term, first, second, third, fourth, fifth. So I'm not going to make you do this very often, but I need you to see that this is a little bit of a hassle. Recursive is not good for this. Explicit is very good for that. Okay, so one I would like you to practice. The check on that would be the next one. So I'll fill out the whole row. So it looks like the pattern is that it's subtracting 8 each time, which makes it arithmetic, it makes it have a common difference. So the part I'm really interested in I'm more concerned about is this is what's new on this page. If you remember that you had to state the first term, and the recursive formula that you state a sub n is the term before it, a sub n minus 1, subtract a. The next any term is equal to the term before it minus a. And if you want to know the seventh term, you can do it manually. The recursive formula doesn't help you. You can do it on the side. That's the explicit formula if you'd rather. I'd say that's probably about the same amount of work. The 7's not very much. You see, I keep all these numbers fairly low, so there's not too many. I didn't ask you to go out to 56 terms and make you do it manually. Negative 65. Okay. So to recap, before we give you the rest of the time to go back and finish up, this is what a sequence is, and the two types you need to be very familiar with. So we practiced identifying those types. Sometimes they're not that, but if you add the same thing each time, it's arithmetic, a common difference. You multiply the same thing each time, it's geometric and common ratio. We practice writing an explicit formula, which this is good to know. This is like the part, the knowledge piece. If you don't memorize this, and then you come up with a formula for geometric on the spot, that's a lot harder to do. You really need to have those memorized on how to get started. Second page, we did the same concept, in opposite order. Gave you the formula instead of you coming up with the formula. And on the back page, we talked about the recursive formula. Hopefully you see that it's kind of a pain for these. Explicit's good, recursive not so much, but it is fairly easy to write. It's easy to understand as long as you're familiar with the notation, as long as you're familiar with what a sub n minus 1 is. Any particular questions that you know that you have that you'd like to get cleared up?